Steve's beautiful handwriting. Much better than mine. But today we are privileged to host our own Kam-Biu Luk, who requires very little introduction, perhaps except to list a long list of accolades that he has received. So I will read part of his CV that Kam-Biu received his bachelor's degree in Hong Kong in 1976 and a PhD from Rutgers in 1983. And he came to us in 1989 and has been here ever since with small sabbatical leaves, I guess. And as I mentioned, the long list of awards and other accolades includes the Outstanding Junior Investigator Awards in '89, a Sloan Fellowship in 1990, Miller Professorship in 2001, and perhaps one of the biggest recognition in American Physical Society, Panofsky Prize in 2015, but perhaps financially one of the biggest recognition is being the co-recipient together with the DIABA collaboration of this year's Breakthrough Prize and being on stage with movie stars. So Kam-Biu is joining us today to discuss his experiments with the reactor neutrinos, and please welcome.
Well, thanks, Yuri, for the nice introduction. So actually, in my talk, I'm not going to cover just DIABA. What I'm trying to do is to tell you, essentially the advancement of the field using nuclear reactor. So I will cover a little bit, say backward in time, back into say the beginning of this millennium, and then of course then I would tell you what's going on right now, and also give you a snapshot of what might happen in the future. So let me start with something that many of you already know. Thank you. So this is what we call the standard model of particle physics. So right now, we know all the ordinary matter we encounter in the universe are made of quarks and leptons, and also some force carriers over here, and many of us also have heard a lot about say the Higgs particle discovered in 2012. But for this talk, the neutrinos, are this the three guys. We call the electron neutrino, which is associated with the electron in interaction, and also then we have the muon neutrino and the tau neutrino. Now, one important thing for us to keep in mind is when we build up the standard model of particle physics, we assume the free neutrinos are massless. So this is one of the foundation of say this model. Now, one interesting thing about the neutrinos is the fact that they are weakly interacting. So as a result, they can go through the matter relatively easily. So we can now turn this the peculiar sorry about that. Because I rebooted the machine. Okay, all right, yeah. Now, because of say the weakly interacting properties of the neutrinos, we can turn it around and use it as a tool to study say some other natural phenomena. So in particular, back into the 60s and early on, we already knew that right at the center of the sun, we had nuclear fusion going on. So if we look at say the fusion process, in particular the four in color, then you'll notice, okay, they all involve the electron neutrinos. And as a result, okay, once they are produced at the center of the sun, and they can essentially, okay, penetrate through the sun and just go everywhere. So if we can, okay, detect them on Earth, then basically, we can use the neutrinos to infer, okay, what might happen, okay, at the center of the sun. So this idea, okay, indeed was carried out by Professor Davis, using an underground laboratory in the Homestead mine. And because the neutrinos are so weakly interacting, you can see that we have to use a very large detector in order to do this experiment. So the way the solar neutrinos are counted is okay, use this reaction. So we have the electron neutrino hitting the chlorine atom inside the bridging solution, and then after reaction, then we have the electron and then the argon-37, okay, coming out. So by counting the number of argon-37 atoms, then basically we'll be counting the number of solar neutrinos. Now this experiment was carried out in the late 60s all the way to say in the 90s or so. Now you can see if we look at the individual data point, it's very hard for us to draw any conclusion. However, if we accumulated over 20 years of data, then at the end we find out the number of solar neutrinos counted in this experiment is totally different from the prediction using say the model describing the sun. So we have to understand what's going on. The why the experiment is so different from the prediction. Then about say the 80s and the 90s, then in another experiment, as a matter of fact, there were a couple of experiments, but say this one I'm going to highlight is the most definitive one. When the super chemical experiment in Japan was set up, they used this to study atmospheric neutrinos. Now the atmospheric neutrinos essentially come from cosmic ray hitting say the atmosphere and then producing the pions and muons. Those are unstable. Then in the end, they decay to give us essentially the electron neutrino and then also the muon neutrinos. Now these neutrinos then can penetrate through a lot of rock and get into say this pure water detector. Then by looking at the signal coming from the electron or the muon neutrino interaction inside the water tank, then essentially we can again count say the number of them. Now one interesting thing about this experiment is when we look at say the number of muon neutrino counted in the detector comparing with the prediction, again you can see when the neutrino is going through the South Pole, going all the way up to say Japan, then we see the less muon neutrino comparing with say the expectation. So why we have say this major disagreement certainly is extremely the puzzling. Now one of the explanation around that time is the neutrino oscillation. So let's see what we mean by that. So imagine say at the beginning we start off with say one type of neutrinos representing by this kind of ghosts. Now if we say wait for a while and then look at say this ghost again, then one of them is changed to another kind. Now if we continue say to watch, then you can see that if they continue to change to the other kind, but we keep on only counting say the original type, then naturally we'll see less than say the what it should be. So this is the essentially the pictorial way to understand neutrino oscillation. And certainly you can see from this picture, it can account for the disappearance of the solar neutrinos and also the atmospheric neutrino. Right now, let's go into a little bit of say details. Now it turns out neutrino oscillation is the consequence of something called neutrino mixing. Now, according to these theoretical ideas, the free neutrinos that we observe in laboratory actually the linear combination of free mass eigenstates such that each one will have a well-defined mass. Then I label here M1, M2, and M3 like this. Now this linear combination is through this mixing matrix, and it turns out this matrix actually depends only on 4 independent variables that we call the mixing angles theta 1, 2, theta 2, 3, and theta 1, 3, and also another the complex phase we call delta. So the values of delta will tell us whether we will have any kind of CP violation or not. We'll get into that towards the end of the talk. Now from these 3 masses, we can then form some new quantities. Usually we call the mass square the splitting, or mass square the difference, and this is the definition. So basically it will be the difference between the mass square of say one type to say the from the other one. For instance, say this is the free one. Now if we have only 3 kinds of neutrinos, then it turns out this mass square differences that can be related by say this equation. So in other words, only 2 of them say are independent. The other one can be deduced from the other one once we have the other 2. Now the more important take home message from neutrino mixing is this will require neutrinos to have mass, and this will be in total contradiction to the standard model, because remember in the standard model we assume neutrinos are massless. So therefore you can see the observation of neutrino oscillation essentially implies the standard model is not complete. Now if we now say use this concept of neutrino mixing to describe neutrino oscillation, then usually we'll end up with say a lot of the expression describing the oscillation probability. So here I show only one of them, describing essentially we start off with an electron neutrino and still end up with say the same type. Now to make life easier, here I approximate the probability only by 2 terms. In particular, we want to look at say the second term here. Now the second term consists of essentially 2 factors. So the first one is the sine square 2 theta 1 3. Now it turns out that if we draw it out, this represents essentially the amplitude of say the oscillation. Now in the second term factor here, then you see we have say the delta m squared appears there, and also the distance traveled by the neutrino, and also the energy of say the neutrino. Now it turns out this whole thing essentially tells us about the frequency of the oscillation, or the wavelength of say the oscillation. So these are the physical interpretations of these 2 factors. So then the question is, do we really sure that neutrino oscillation is the right explanation? And it turns out the most decisive experiment came from the Snow experiment in Canada. They used 1 kiloton of heavy water to detect say the neutrino coming from the sun. Now the reason why we use heavy water is so that we can essentially use 4 reactions given by this 4 diagrams to identify the nature of the incoming neutrino. So for instance, if we look at say the 2 reactions involving say the W boson, this is what we call the charge current, then only the electron type can have say this reaction. However, for say the other 2 reactions involving say the neutral Z gauge boson, then this neutral currents essentially will tell us the number of neutrinos coming in, disregarding say the types we have Now, using these 4 reactions, then essentially, then we can measure the flux of the electron type versus say the flux of say the other 2 types. Now, from the result, in the end, they find the number of electron type is given by this number, and then for the other 2 types is say this amount. So when we add them together, this is about 5 million per centimeter square per second. And whereas if we use the best model describing the sun, then you can see the prediction indeed is consistent with the experimental observation. So this is the really say the a big milestone for say the neutrino oscillation. So that's the reason why this awarded the Nobel Prize last year. So then the question is in addition to using the solar neutrino and atmospheric neutrino to study neutrino oscillation, can we use other methods? So it turns out on Earth, one of the very convenient source of the neutrino, to be more precise, antineutrinos can be obtained from nuclear reactor. So for a running nuclear reactor that can generate about say the 1 gigawatt of electricity, it turns out it can generate somewhere around 6 times 10 to the 20th neutrinos per second. And this antineutrinos basically are coming from the nuclear fission process inside say the nuclear core. So you can see from the fission process we produce a lot of unstable nuclei, and when they the beta decay, then they give us essentially the electron antineutrino like this. And because we have such a strong intense source, so as a result, then we can use that to do experiment. So the first the successful experiment observing the neutrino oscillation using nuclear reactor is the Kam-Biu experiment, which was done at the beginning of say this millennium. This is the map of Japan, and it turns out in the Japanese Alp, there's a mountain which is 1 kilometer in height. Inside this mountain is say the Kam-Biu experiment. So the Kam-Biu detector is mainly made of 1 kiloton of liquid scintillator for detecting the antineutrinos. Now, by the stroke of luck, this detector is surrounded by all the Japanese nuclear reactors popular everywhere before say the major earthquake occurred several years ago. Now, even though all the Japanese nuclear reactors are spread out, however, if you look at say the antineutrinos emitted by them and got detected by the Kam-Biu experiment, then basically most of them will come from a distance roughly about 180 kilometer. So this is really say the stroke of luck here. Now, the way we can detect the antineutrino is through this reaction, because the liquid scintillator usually is a hydrocarbon. It's very rich in hydrogen, or in our case this will be the protons. Now the reaction will give rise to the positron and a neutron. Now the electron usually inside the liquid scintillator will slow down very quickly, giving up its energy as a burst of light, and then in the end you will annihilate with the atomic electron inside the liquid scintillator to give you 2 gamma rays, and then these 2 gamma rays again go through the liquid scintillator, will essentially lose its energy through the many different processes to give rise to a burst of light. Now then for the neutron, then it will not collide with the proton elastically, and give up its kinetic energy, and then in the end, then for Kam-Lan, then it will capture by the proton in the liquid scintillator. So forming a deuterium with an emission of a monoenergetic gamma ray of energy 2.2 MeV. Now this is the positron will give you a signal essentially right after the collision or the interaction. So that's why usually this is give you so-called a prompt signal. And then for the neutron, because it has to lose its kinetic energy by say some collision before it gets captured. So usually it will take some time. So for instance, for the Kam-Lan experiment, on the average, this will occur roughly about 180 microseconds. So that's why this is called delay. However, because of the correlation between these two signals, then this will be a very distinct signature for identifying the anti-neutrino reaction. Now, in the later experiment, for instance, like diabase, then we do not use just pure the hydrocarbon to capture the neutron, but we put in a little bit of gadolinium to enhance the chance to capture the neutron, and also shorten the capture time from 180 microseconds down to about 30 microseconds. So this is important for us to beat down the background. So this is how we count the reactor antineutrinos in Kam-Lan. So in the end, this is what Kam-Lan has observed the energy the distribution of the antineutrino. As a matter of fact, just using the positron energy, which is directly coupled to the antineutrino energy. So you can see the data points certainly have a very different behavior comparing with say the expectation if there's no neutrino oscillation. So this is essentially a very clear evidence. Indeed, under control condition, we still observe the neutrino oscillation. Now, from say the measurement, if we interpret this as neutrino oscillation, then using the formula we described in a previous slide, then we can essentially extract values for the mixing angle theta 1, 2, and also for say the mass square difference, the delta m square, the 2, 1 or 1, 2 here. All right. Now, if we now fast forward to 2011, then this was the situation regarding say our knowledge of the mixing parameters. So from atmospheric neutrino and also from accelerator experiments, then we concluded that the mixing angle theta 2, 3 was about 45 degrees, which is still not true up to this moment. And then from the solar neutrino experiment and also from the Kam-Lan experiment, then we know the theta 1, 2 is about say 34 degrees or so. Then the question is what happens now to say the theta 1, 3, and also what is the values for this CP rioting phase delta, and also among the three masses, which one is the heaviest? Is M3 the heaviest, or is it the lightest? So this is normally what we call say the normal mass hierarchy, and this is the inverted mass hierarchy. So a few years ago, basically these were the three the open questions that we didn't know about neutrino oscillation. Now among say this three unknown quantities, it turns out theta 1, 3 is the most important, because it turns out it dictates how lightly we can measure the other two. So now how do we say measure theta 1, 3? It turns out there are two ways. One is we can use accelerator. However, that experiment will not give us a very clean measurement of theta 1, 3. On the hand, if we use nuclear reactor, then it turns out we can measure theta 1, 3 unambiguously. Now, if we now write out a little bit more details about the oscillation probability for the electron anti-neutrino, then you can see there are two terms. The first term depends essentially mainly on theta 1,3. If we graph it out as a function of the baseline, then this term will give you the oscillation pattern given by the green curve here. So that tells us theta 1,3 will have the maximum oscillation occurring about 2 kilometers from a nuclear reactor if we want to do the experiment. Now, whereas for the second term, it dictates essentially by theta 1,2, and which is representing by this blue curve here. And Kamlan, just to remind you, essentially was sitting somewhere over there. All right. Now, on the hand, if you go to 2 kilometers, then you can see basically this term doesn't really contribute much to this expression. So that tells us essentially when we measure theta 1,3 using this distance, we can really have a very pure measurement of theta 1,3. Now, in order to beat down the systematic uncertainty and also the control the detector uncertainty to the minimum, then in the current generation of reactor experiments, normally we have two groups of detectors. One is called a near detector, which is closer to the reactor. This is used to essentially determine the flux coming out, the flux of anti-neutrino coming out from the reactor, and then from there, then essentially then we can deduce what we should see in the flat detector, and then compare with the actual measurement. So this is the working principle of these 3 experiments which are ongoing. So the 3 experiments are called the double show in using the show nuclear power plant in France, and then the Reno using the power plant in South Korea, and then the Daya Bay experiment using the Daya Bay nuclear power plant. And if you look at the comparison of these 3 experiments, then you can see Daya Bay has the most powerful nuclear power plant for the experiments. So that translates to we have a very intense the anti-neutrino source comparing with the other 2. And also if you look at the target of the Daya Bay, in particular the far side, which is the near the oscillation maximum corresponding to for theta 1,3, then Daya Bay has the 80 ton of target mass. Whereas the other 2 experiments, you can see they are a lot less. So as a result, the Daya Bay essentially is leading the race. And furthermore, if you look at the amount of rock covering the detector, essentially to eliminate the amount of cosmic ray interaction in the detectors, Daya Bay again is the best. So since I'm working on Daya Bay, so let me just say a few more words about the experiment. So the Daya Bay, the nuclear power plant, is located about 55 kilometers from the Victoria Harbour of Hong Kong. Or if you have been to Hong Kong, the airport is about 70 kilometers away from the power plant. Now, when we get to the site, this is what we see. There are 3 nuclear power plants actually inside this complex. So the 2 the closer to us is called the Daya Bay nuclear power plant, and then about a kilometer to the east is the so-called the Ling Ao nuclear power plant 1 and 2. So altogether there's 6 nuclear reactors, and they have identical design and equal power. Now the important thing for you to notice is the mountain is right by okay, say the power plant. So as a result, this is okay an ideal site to build okay an underground experiment. So this is okay the what we have the layout for say this experiment. So the 6 nuclear cores are over here representing the black dots, and you can see from the satellite picture the entrance portal of our experiment. So this the blue thing is say this is blue roof of the entrance portal. Now on either side of our entrance portal, we have 2 buildings. One is the building that we use for assembling our the detectors, and then after we assemble them dry, then we truck them into our tunnel, which is representing say by this blue lines here. So all together we have the 3 underground halls. We call them this one EH1, which is used to monitor the anti-neutrino flux coming from mainly the Taipei nuclear power plant. And in order to monitor the anti-neutrino flux from say the Ning'ao nuclear power plant, then we have another one which is called EH2. And then about 2 kilometers into say the mountain, then we have say we call the far site. Now if you look at say these 3 sites, basically we can tell say the number of reactors we can accommodate in each one. So we have 2 here, 2 here, and up to 4 over there. So this is the the configuration. Now if we look at each experimental site, then this is what we see. Essentially we have a big giant swimming pool which is about 10 meter tall, and for say this near site, this is about 10 meter wide also, and then about say 15 meters or so in length. Now inside the water pool, there are 2 anti-neutrino detectors. The important thing for you to notice is each the anti-neutrino detector has a target mass of 20 ton of a liquid scintillator, and I said before. This time, we doped it with a small amount of gadolinium to enhance the chance of capturing the neutron with good efficiency. Now, the reason why say that the anti-neutrino detectors are submerged inside a water pool is that we want to use the water to absorb any kind of radiation from the surrounding rock, and also if you have cosmic ray going through. They can generate the neutrons that will mimic say our signal. So therefore we use water to degrade say the amount of the neutrons coming from the cosmic ray interaction. And also using the water pool, then we can instrument with the photomultiplier tubes to essentially tag the incoming cosmic ray muon as well. Now, the experiment was set up towards the summer of 2011, and then by the Christmas Eve of 2011, then we started the data taking with 2 detectors in the EH1 near hall, and then 1 in EH2, and then 3 in the far hall. Now, with this 6 detector, we took data for roughly about 55 days, and surprisingly, when we look at say this the small amount of data, we observe essentially some of them disappear. As a matter of fact, from this number here, that tells you that essentially 6% of the electron anti-neutrino from the reactors that disappear. And if we look at say the number of say the detected anti-neutrino as a function of say the baseline, then you can see for the near hall indeed the amount of say the deficit is small. However, by the time we got to say the far hall, then we saw certainly as something very significant. And from say this deficit of electron anti-neutrino, then we deduce is the values for theta 1 3, or say in terms of the amplitude of the oscillation, we obtain essentially a number like this. And this if you look at the errors, then basically that our result is more than 5 standard deviation significant. So as a result, then we reported that we have a discovery in 2012. Now, to convince that indeed we are seeing the real neutrinos coming from the reactors. So what we can do is we can look at essentially the rate of the number of the rate of anti-neutrino interaction as a function of time. So you can see for the two near sites, the observed number or the observed rate is consistent with say the expectation essentially derived from the nuclear power or the electricity provided by say the power plant. However, by the time we get to say the far side, you can see the prediction certainly is not quite the same as say the measurement. The measurements are always lower. So this convinces us that indeed we are seeing something real. Now, of course, the nice thing is we have the other two experiments also cross-checking. So in particular, Reno, they have also 6 nuclear reactors in a line, and also they have a relatively say the large target mass, even though it's still smaller than diabetic by quite a bit. However, this 16-ton detector can give them quite a bit of statistics. So shortly after diabetic reported the discovery of a non-zero theta 1 3, then Reno also reported their first result. And again, you can see they observed roughly about 8% of the anti-neutrino from their reactors disappear. And from their disappearance, then they obtain a sine squared 2 theta 1 3 value, essentially consistent with what we obtain in diabetic. So this is certainly extremely comforting. So this indeed a good year for the particle physics, because it was also 2012 the year the Higgs was discovered. Now, if we now move a little bit closer to the present, the double show after they obtained data for a couple of years using only the far detector, because the near detector was not ready until only about last year. So they could only essentially use the one detector to obtain the measurement. So you can see after some year, basically they have also say observed some of the anti-neutrino disappear. Now, however, because they did not have the near site, so as a result, they have to rely on the theoretical calculation to predict what they see. So as a result, you can see they have larger the systemic uncertainty. So which is reflects in the error bar. So you can see comparing with diabetic and also the Reno, certainly the double show result is the worst one. All right. So after say this discovery of non-zero theta 1 3, certainly we are not going to just stop there. We continue to push the measurement. So for instance, for diabetic, after we reported the discovery, then in the summer of 2012, then we stopped the experiment for a few months. So then we installed the last two the anti-neutrino detectors into say the experimental hall. So now in this picture you can see all 8 of them, and also we took advantage of this period to determine the energy response of our anti-neutrino detector as well as we can. And from say this special measurement, and also using all say the 8 detectors, just towards the end of last year, then we updated the measurement of theta 1,3 this way. So you can see now in this case, based on roughly about 600 days of data using 6 detectors as well as 8 detectors together, then you can see the error bars are a lot smaller now, and certainly is this is very beautiful. And also now with very good the measurement of our energy response, we can also now utilize essentially the entire energy the distribution to determine the mixing parameters. So we can see now in this case, indeed, the data points lower than say the expectation if there is no oscillation, or if you take the ratio, then you see the pattern very clearly. So from this the set of data, then now we obtain essentially the most precise measurement of sine squared theta 1,3. Now you can see essentially this is about a factor 3 better than our first say measurement. Now more importantly, besides measuring now the amplitude of the oscillation due to theta 1,3, we also now essentially obtain the frequency of say this oscillation, this which is represented by this symbol delta m squared EE, and this is essentially the value now we obtain. Now, if rather than looking at the energy distribution or this part as a function of just baseline, but now if we say turn it around, look at say the oscillation probability as a function of L over E. If you remember the formula, L over E essentially controls the frequency as well, along with delta m squared. Then you can see say the beautiful the oscillation pattern from diabase. And then the nice thing is now Kam-Biu also has done this a while back, and you can see from reactor and anti-neutrino experiments, basically we have very clear evidence of say the oscillation pattern, and it's really, really nice. And just a couple of days ago, Reno also reported say the new measurement based on say a larger sample. So in the case of say 800 days or so, and again now you can see the pattern, and also if you look at say the sine squared 2 theta 1,3 and also the delta m squared EE obtained by Reno, then you can see the Reno's result now is converging to say the one obtained by diabase. And so again this is really good the having experiments cross-checking each other. So if we now look ahead, this is the what we expect to see for theta 1,3. So for diabase, we are going to continue to take data until essentially the end of 2017. That is about 2 years from now. And right now we are somewhere here, as far as data collection is concerned. And our projection is by the time we finish data taking, the data set will give us a precision on sine squared 2 theta 1,3 down to say 0.03, which is roughly about another factor of 2 improvement comparing with what we have just published recently. And then for Reno, they have been working very hard in reducing the systematic uncertainty, and their expectation is by the time they are done, which is also around say 2017 or so, then the precision on sine squared 2 theta 1,3 will be about 0.05, which is what the diabase has obtained at this moment. Now for double show, as I said, they have the near detector now running, so they are taking data with both near and far detector together, and the expectation is by the time they are done with the experiment, then in the best scenario they can measure sine squared 2 theta 1,3 to about 0.0 1 or so. So which is certainly the a lot worse than say the other two. So the hope is in the future, the three experiments, okay, can work together and combine all our results so that, okay, we will provide, okay, say the best measurement of, okay, science square, theta 1,3, okay, for the community. So this is, okay, essentially now the story of, okay, theta 1,3. So as I said, okay, say theta 1,3, okay, is very important for neutrino oscillation program. Is, okay, given, okay, by, okay, the following few slides. So recall, okay, I mentioned that actually we can measure theta 1,3 also using, okay, the, say the accelerator experiment. Now, right now, okay, there's one experiment, okay, T2K, okay, in Japan, and also another one called NOVA, okay, in the US. Now, for the T2K, okay, they have just, okay, published something recently. Now, because in that experiment, they start off with a muon neutrino, and then they look for, okay, the appearance of electron neutrinos, okay, in the detector. So this kind of appearance experiment, it turns out has a very messy, formula that depends on the CP routing phase, sine squared 2 theta 1,3, and also, okay, the mass hierarchy, whether we have, okay, say one or the other. So as a result, okay, by, okay, T2K itself, they cannot really, okay, uniquely pinpoint, okay, sine squared 2 theta 1,3. Now, however, because now the reactor experiments have measured, sine squared 2 theta 1,3 for them, so as a result, they can, utilize, okay, this result to extract something about, okay, say this, okay, CP routing phase. So if we look at, okay, say the result, then basically it tells us this. The values for the CP phase, okay, is unlikely to be, okay, between, okay, 0 to, okay, 1. This region now, okay, is sort of ruled out. And that tells us, okay, essentially, okay, delta CP, we should have a value likely, okay, in this region. As a matter of fact, based on, okay, say this, okay, the very first attempt, the preferred value for theta 1,3 for delta CP is about, okay, minus 0.5. And also, if you really want to push, okay, say to the limit, then you may say, well, there's a hint that the mass hierarchy, okay, would be, okay, say the normal one versus, okay, in favor of, okay, say okay, say the inverted one. But at this moment, okay, I think it's still too early, okay, to say. All right. Now, because now theta 1,3, okay, is known to be non-zero, then it turns out now it will allow us to determine the mass hierarchy using, okay, nuclear reactor. So at this moment, there are two experiments, okay, being designed or under construction. So one of them is called, okay, the Juno experiment taking place, okay, in China. So what they do now is, okay, they will utilize, okay, two new nuclear power plants, okay, in China, which is about the 200 to 250 kilometers, okay, from Hong Kong, which is over here, and then about 50 kilometers from the nuclear power plant, they are constructing a new underground, okay, the experimental hall, which is, okay, 700 meters okay, deep underground. And then in there, they plan to build a new detector, which is gigantic, okay, 20 kiloton filled with a liquid scintillator. So the idea is this: at this, okay, distance, the oscillation pattern will be determined by, okay, theta 1,2, which is, okay, to say this, okay, say the profile. However, because of say the theta 1,3 term, then if you recall, okay, we have, okay, say the delta m square EE, okay, the effective, okay, mass square splitting. If we, okay, work through, okay, say the calculation a little bit more carefully, then it turns out, okay, this, okay, delta m square EE depends on, okay, the mass hierarchy. So if we have, okay, say one, say the normal mass hierarchy represented by the blue line, then the theta 1,3 term will give you, okay, say some kind of small, okay, so oscillation pattern riding on top of, okay, say the the profile dictated by theta 1, 2. But on the hand, if we have the inverted mass hierarchy, then you can see there's a shift in position for say the small theta 1, 3 oscillation pattern. So the goal of the experiment is to try to measure all these small oscillation peaks as precisely as you can. And then from there, then you can then deduce what mass hierarchy you should have. So we can see from this pattern, it's a very challenging problem. However, it doesn't stop say the physicists from tackling the problem. Now the other one, which is also try to address the same thing. The graph it disappeared. Now this is the Reno experiment. So about say 50 kilometers away from the nuclear power plant. So the Reno collaboration is trying to do something similar to say the Juno experiment, build a new underground facility and put in also a very gigantic detector. This is 18 kiloton liquid scintillator detector. Try to also measure the mass hierarchy. And both experiments plan to start in 2020 to 21. So which is about 5 years from now. And then in order for them to give us an answer, they have to run the experiment somewhere from 6 years to 10 years. So it takes a long time in order to get an answer. Now, the last thing I want to tell you is because theta 1, 3 is not zero, therefore now we can plan another new experiment to find out whether say neutrino oscillation is the same as say the anti-neutrino oscillation. So this is essentially what we call say the CPU ovulation. So the idea is from Fermi Lab in Illinois, we will prepare a very intense muon neutrino beam, and shooting 1,300 kilometers away to South Dakota. This is the home state mine, but now it's called SURF. And look for say essentially the appearance of the electron neutrino. And at this site here underground, there will be essentially a gigantic experimental hall that can house essentially 4 detectors. Each one is 10 kiloton using liquid argon. So once we have this experiment, then we will first do say this part, and then after that change it to anti-neutrino, and then repeat and see whether we see any difference. If say we can do this experiment, then hopefully this will give us a hint of whether say neutrino ultimately is tied to say the big issue, that is why the universe is dominated by matter, and the anti matter say for some reason disappear. And of course because we are made of matter, so this will essentially link up to our existence. So basically this is the end. So I hope that in this talk now you find out neutrinos are very interesting. They can change say their identity, and also after all they have a small mass, and also this is say the first piece of evidence indicating that there's new physics beyond the standard model. Thank you.
Questions for?
So I understood that you talked about only differences in mass. Could you put limits, terms of limits on the actual values of the mass?
No, because if you look at the formula, it depends only on say the mass square difference.
Are there other experiments that could?
Yes, for instance, there's one experiment called Katrine. Actually, some of the Berkeley at LBL are working on that. So they will use the tritium to determine the absolute value.
question?
So a couple of years ago, there were reports of anomalies in the neutrino spectrum from a reactor. This bump seen by
Yes.
Reno and
Right.
you guys. What's happened with that? And also, generally, how well do we? How much of a limitation is our lack of knowledge of the neutrino spectrum?
Well, certainly you can see, okay, from double show, they have to rely on the theoretical prediction. So in that case, certainly they are very sensitive to that. So that's the reason why they have very large, okay, the systematic uncertainty. Now, however, for the Taipei and also for Reno, since we are using, okay, near and far, so doing a relative measurement, so all this, okay, say, common, okay, the systematic, okay, will cancel out. So therefore, in our case, okay, essentially we are insensitive to, okay, say, this uncertainty.
Is the bump still there?
The bump is still there. As a matter of fact, you can see it, okay, from the double show result, right? So you see, okay, the bump is there. Because now notice, because okay, the prediction will give them, okay, a relatively smooth, okay, say the say description. So that's why, okay, the bump, okay, is very clearly shown. And certainly the Taipei and Reno, okay, have seen this. As a matter of fact, we have a paper which was supposed to be online today, but the PRL just changed it to 2 days later. So otherwise, I can show you. Yeah.
So maybe an oddball question, but for neutrino oscillation, for not to be an energy eigenstate, there has to be some delta T, I think, to allow the oscillation. I think I remember that in solar neutrinos, that delta T comes from uncertainty of energy and the reaction of the sun. For the reactor neutrinos, whenever that delta T comes from to allow the oscillation.
Well, I mean, one idea is, okay, if you describe the neutrino with a wave packet, then the delta E will come from there.
I just
But-
say, here's delta Q for the reaction that happened in the reactor. And some energy from the electron went into the
Relatively, yeah.
core, and the remaining energy is that of the neutrino. Where is you get enough delta Q remaining for the oscillation?
I haven't thought about that because we did look into, say only the wave packet, the delta E. But okay, I haven't thought about, okay, say when, okay, that might come from, say in the nuclear reactor. Maybe Vic, can you help?
You're right. The wave factor is not a defined energy in the first place.
Yeah.
It's a combination of both momentum and position are
And in fact, I think Zoltan published a paper
Yes.
describing this in a purely covariant way, where you don't need to say
Right.
delta E or delta T. It's a
Right.
purely covariant description for it. That's what we mentioned. Any other questions? Let's thank you again.